In this video, we'll be looking at the moving average model. A moving average term in a time series model is a past error multiplied by a coefficient. Rather than using past values of the forecast variable in a regression, a moving average model uses past forecast errors in a regression-like model. Thus, the equation of a MA model of order Q, also written as MAQ model, can be written as yt is equal to c plus summation of I equal to 1 to q theta I epsilon t minus I plus epsilon t. In this equation, yt is the prediction at the current time step. Theta I is the coefficient of error of the ith time step before the current one. Epsilon t minus I is the error at the ith time step before the current one. Epsilon t is the white noise at the current time step. Q is the number of errors taken into consideration for the MA model. Let us use the MA model on a sample time series data. Real life data can be modeled in the same way.
A new cake shop just opened. The owner of the cake shop wants us to estimate the number of cupcakes she should produce so as to maximize her profits. To achieve maximum profits, we would like to maximize the number of cupcakes sold and also minimize the wastage. So we would like the number of cupcakes produced each day to be equal to the demand of the cupcakes. This shop only sells fresh cupcakes. That is, any cupcake sold should have been made on the same day. Any unsold cupcake at the end of the day is considered wastage. We decide upon a moving average model, or MA1 model in particular, for making our predictions. The equation for the MA model is yt is equal to mu plus c1 et minus 1. Here mu is equal to 10, c1 is equal to 0.5. Et minus 1 is the difference between the demand and the produced cupcakes in the previous time step. Yt is the number of cupcakes that will be produced in the current time step based on our prediction. On the first day, we consider the error at the previous time step as 0 and produce cupcakes equal to y1. Therefore, y1 is equal to mu equals 10. So 10 cupcakes are produced. At the end of the first day, the shop owner informs us that the number of cakes sold that day were 8. Therefore, the number of cupcakes required were actually 8, but we produced 10 cupcakes. Thus, error at the first time step, that is E1, is equal to 8 minus 10, that is equal to minus 2. On the second day, we use the error of the first day to predict the number of cupcakes that should be produced. Therefore, y2, that is equal to 10 plus 0.5 into E1, where E1 is the error incurred on the first day. Therefore, y2 is equal to 10 plus 0.5 into minus 2. Therefore, y2 is equal to 9. Therefore, on the second day, we produce 9 cupcakes. At the end of the second day, the owner informs us that 10 cupcakes were required, but we just made 9 cupcakes. Therefore, we made 1 cupcake less. Therefore, error at the second day is equal to 10 minus 9, that is equal to 1. On the third day, we use the same equation of moving average model to calculate the number of cupcakes that need to be produced. Therefore, y3 is equal to 10 plus 0.5 e2. Therefore, y3 is equal to 10 plus 0.5 into 1. Therefore, y3 is equal to 10.5. We consider that fractional values are also valid for this example. At the end of the third day, we are informed that the cupcakes that were required were 10.5, which is equal to the number of cupcakes that were produced on that day. Hence, E3, which is the error on day 3, is equal to 10.5 minus 10.5, that is equal to 0. On the fourth day, we calculate the number of cupcakes to be produced. Therefore, y4 is equal to 10 plus 0.5 into E3. As E3 is equal to 0, y4 is equal to 10 plus 0.5 into 0. Therefore, y4 is equal to 10. At the end of the fourth day, we were informed that the number of cupcakes required that day were 12. Therefore, error at the fourth day is equal to E4, that is equal to 12 minus 10, that is equal to 2. On the fifth day, we calculate y5 is equal to 10 plus 0.5 into E4. Therefore, y5 is equal to 10 plus 0.5 into 2. Therefore, y5 is equal to 11. At the end of the fifth day, the required number of cupcakes were 12. Therefore, error at the fifth day is equal to E5, that is equal to 12 minus 11, that is equal to 1. The If we plot our predicted values versus the actual requirement of cupcakes, we can see that it is a pretty close fit. Thus, we can conclude that MA model can be used successfully to model time series data.
We were arbitrarily choosing the value of q. ACF plots provide a statistical way to choose the order of the moving average model. Autocorrelation is the relationship of a variable with its previous time period values, also called as lags. It is represented by Pearson's correlation coefficient, which has a value lying between -1 and 1. In ACF, direct and indirect effects of values in previous lags are considered. Here is a sample autocorrelation plot. We can see that only the previous time step has a significant correlation. So we can model it as a MA1 model whose equation looks like yt is equal to c plus et plus theta 1 et minus 1, where et minus 1 is the error term in the previous time step. Coefficients of the MA model can be found from the autocorrelation function. For further reading, you can use the additional resource. Now that we have a good understanding of the MA model, let's use it on a sample dataset. Real life data can also be modeled in this way.
An online cab service has consulted us to improve their profits in a certain region. To maximize the profits, the cab service should allot cabs equal to the demand in that region. Therefore, our task is to predict the demand so as to allot the cabs accordingly. The cab service already did a survey on the demand for cabs in that region. We plot the autocorrelation plot of this data. As we can see in the plot, only the previous time step has significant correlation coefficient. Hence, we can model the data with a MA1 model. We find the equation for the MA1 model. The equation is yt is equal to mu plus c1 et minus 1. Here, yt is the predicted number of cabs which will be required in the current time step. Mu is equal to 4 and c1 is equal to 0.5. Mu and c1 are constants. Et minus 1 is the error in the previous time step. Et minus 1 is equal to the difference of the actual demand for cabs and the prediction of the previous time step. For the first day, we consider the error at the previous timestamp as 0. Therefore, E0 is equal to 0. Therefore, we supply cabs equal to y1, where y1 is equal to mu is equal to 4. At the end of the first day, we find that the actual demand for cabs was actually 10. Therefore, error on the first day is equal to 10 minus 4, which is equal to 6. On the second day, we use the error of the first day and allocate y2 number of cabs. Therefore, y2 is equal to 4 plus 0.5 into e1, where e1 is the error on the first day. Therefore, y2 is equal to 4 plus 0.5 into 6. Therefore, y2 is equal to 7. At the end of the second day, we get to know that the actual demand for cabs was actually 14. Therefore, the error for day 2 is equal to e2, which is equal to 14 minus 7, that is equal to 7. On the third day, we supply cabs while taking into account the error incurred on the second day. Therefore, the cabs supplied on the third day, which is y3, equals 4 plus 0.5 into e2, where e2 is the error incurred on the second day. Therefore, y3 is equal to 4 plus 0.5 into 7. Therefore, y3 is equal to 7.5. For this example, we also consider fractional values to be valid. At the end of the third day, we find out that the actual demand for cabs is 9. Therefore, E3, that is the error on day 3, is equal to 9 minus 7.5, that is equal to 1.5. The number of cabs supplied on day 4 is Y4. Therefore, Y4 is equal to 4 plus 0.5 into E3. Therefore, Y4 is equal to 4 plus 0.5 into 1.5. Therefore, Y4 is equal to 4.75. The actual demand for cabs on the fourth day is 7. Therefore, the error on the fourth day is E4, that is equal to 7 minus 4.75, that is equal to 2.25. If we plot our predicted values versus the actual demand for cabs, we observe that our predicted values are able to follow the trends of the actual value. So we can use the MA model for predictions.
In this video, we looked at the moving average or MA model. In the next video, we'll be looking at the ARIMA model.